Characterization. The title of the research is Characterization of the Relationship Soil Density and Simple Compression Resistance of Silty soils. We are delivering some information regarding the characterization of this type of soils under triaxial compression test and some information regarding the correlation between these two properties in soil mechanics. So, it is important to recognize that the shear strength or shear resistance as a fundamental property of soils that is taken into account when designing any geotechnical structure can be predicted and understood under equation number 1, which is actually one of the fundamental equations and properties of soil mechanics when it comes to designing any geotechnical structure. In equation number 1, the left side is the shear strength of soils, and the right side depends on the confining stress on which the soil is subjected to, the friction angle, phi, and the cohesion term C. The parameters phi and C depend on the type of soil, the drainage condition, and several situations on which the soil is going to be subjected to. The recommendation is that we determine those parameters once we sustain and subject the soil to those to the conditions that is going to be subjected to. Only on that conditions we can know and we are going to be able to show good parameters for predicting what we want to predict. Figure 1 is the Mohr circle that is represented for the conditions on which geotechnical structures are not confined. We see that this Mohr circle starts the minor stress on the origin. That means that actually the soil is not being confined. We can see that the strength of this soil is actually constant, as it is represented by the straight line on the top of the circle. Sigma 1, which is actually being selected here at the right hand side of the circle, represents the stress that the soil is being subjected to, the confining stress that the soil is being subjected to, and this is actually the stress that the geotechnical structure is subjected soil to when it comes to represent the tensile strength of soils. So in this case, this Mohr circle is more appropriate to represent the tensile strength of soils whenever it is subjected to any stress combination that doesn't subject the soil to any confining stress. In order to stress the soil, we have used the triaxial compression device that is on the screen in figure 2. This triaxial compression device is able to record and to control the stresses mainly the strains that the soil is being subjected to. In this screen we can see a sample, the sample that has been put inside the soil, inside the triaxial compression device. It is a 10 centimeters soil sample and 5 centimeters diameter soil sample that is cylindrical, of course, and it has been put in the triaxial compression device. Of course, there is no confining stress because we are going to subject the soil to a simple compression test, and this configuration allows us to reproduce the stresses that we want to know. One of the main things of this research that is needed to be understood is that we want to predict what is going to be happening with the soil with different densities. It is very important to recognize that the densities, of course, introduce certain gathering of soil particles depending on how big is this density. So several it's going to be very important to understand that this density is very important for the prediction, of course, of the shear strength, because we want to reproduce and to the behavior of the soil. It is going to be very important to have a suitable soil mixture that allows us to handle it and to use it and to build the soil sample in the triaxial compression device. One of the main challenges was to build up a soil sample that was totally homogeneous. So because the soil moisture, sometimes if it was so big, if it was a large moisture, it tended to put the soil sample in a certain moisture content that didn't allow so well to build up and to manufacture, as it can be said, a soil sample that we could put in the triaxial compression device. Anyway, the soil is a highly compressible silt. It is a MH, as the soil classification system allows us to do so. It is a soil whose expansion and compression characteristics is expected to be high, and because of this, we wanted and we was to use this as this particular soil to use in the research because of the characteristics of compression. As it had been said, we want to understand the relationship between the soil density and the simple compression of the soils built up at any moisture content. So one of the things is that we began using and analyzing the strength of the material under a certain constant moisture content. We put the soil in a moisture content of 15%, which is actually a very initial approach in order to study and to develop the identification of the behavior of the material. We put the soil inside a mold, and because of this mold was able to be torn apart, as it can be seen in figure 4. We were able to put the soil in several densities, compressing it more and more in order to achieve the 13 kilonewtons per cubic meter, the 15 kilonewtons per cubic meter, and the 17 kilonewtons per cubic meter, in order to study the relationship between the soil density and the simple compression of the soil samples. So these are 3 samples that were subjected to simple compression test. The 3 samples, one on the left-hand side of the slide, was subjected to 13 kilonewtons per cubic meter, the other ones to 15 kilonewtons per cubic meter, and the right-hand side to the hand side sample was put to 17 kilonewtons per cubic meter. All these 3 samples were subjected to simple compression test, and we can see very interesting results here on the failure mechanism that was developed for the sample, all the 3 samples. We can confirm here that the inclination of the failure was very similar to each other. confirming here that actually we can expect the same shear strength parameters for all three samples. And figure 9 represent the mechanical behavior of the samples at different densities. We can see a continuous line and a dotted line that they were developed in order to confirm that the tests were correctly done. These two series of lines on each figure represented mechanical behavior of and they were performed only on the purpose of identifying whether the test was correctly being done. In figure 10, we have plotted the relationship between the soil density and the maximum deviator stress that the soil samples have experienced. We can see here that the soil density of 13 kilonewtons per cubic meter sustains lower stress than the maximum deviator stress experienced by soil samples fabricated and at a higher soil density. It is very interesting here to see that there is no linear correlation between these two properties of the soil samples. That is, we can see that there is no use and there is no hope of trying to predict the maximum deviator stress experienced by soil samples as a linear correlation. There is a non-linear correlation here. We can see that actually has a clear form of equation represented here for the particular soil that we have used, where the maximum deviator stress, which is actually the maximum compressive stress or simple stress conditions, is represented better by a non-linear relationship. This linear relationship needs two parameters in order to calibrate it. We have experienced and we have learned that 0.001 as the first constant of the non-linear relationship and 0.5507 as the other constant are the parameters that best fit the equation that we propose as the equation that represents the relationship between these two properties of four soils. This result, of course, needs to be confirmed by many other stresses on simple compression tests for the soils that we need to determine in the field, whose strength and compressive stress resistance is going to experience the material in the field. However, it is very important here to recognize that this correlation, if it is fitted to the experimental results on the laboratory, we can predict the maximum deviator stress that the soil sample is going to sustain in any field conditions under any soil density. Many conclusions can be drawn into the table in order to conclude some very interesting observations. For example, the semi-empirical correlation that was being established tell us that there is a one-to-one correlation, which is a very interesting result, because with this result we can actually predict the mechanical behavior that the soil is going to have on any situation regarding the soil density. So if we want, for example, to predict the mechanical behavior of the soil in any conditions of density, for example, when we are compacting the soil material for the base materials of a highway, we can predict the mechanical behavior of these materials if it is put on any soil density. Another very interesting result is that the physical nature of the soil failures were very similar in the soil samples, which is actually one of the main features of the soils, which tells us with the background of the soil mechanics theory that the samples, that the soil is going to behave in a very similar way, which means that the friction angle and the cohesion are very similar, and it only depends on the nature of the soil particles and how they shear each other. Of course, and as has been told, future work needs to consider the behavior of these materials under greater densities and, of course, different moisture contents, and in order to corroborate the empirical law of variation of the material strength with its density. More important is to use several types of soils and put them in very different conditions, and in order to confirm that the empirical relationship that is being proposed can be used, that is that we only need two constants in order to establish a correlationship between the density and the simple compressive strength of the material in order to predict the mechanical behavior of the material under different densities. So this goes up to the end of the presentation. We want to put some references on the table that we have consulted in order to